Hi everybody, it's Mrs. Hanger with Pagosa Springs Middle School Science 8th grade distance learning. This is part 13 of our distance learning series, but it's only part 3 of our chemistry basics. We're still looking at the historical development of a model of an atom. We began back in around 400 BC with Democritus, did a huge leap of time up into the early 1800s with John Dalton, and now we're going to jump even yet another century into our timeline with a very special character called J.J. Thompson. J.J. was a physicist in Britain. Seems like we've got a lot of scientists from Britain who have been very key and instrumental in the development of the model of an atom. There's a lot that I could say about J.J. Thompson. You'll see. He's a very interesting person. One thing, though, is though he made his entrance on our timeline in the early 1900s, his contributions are not just his own study, but in the fact that he trained up and collaborated with the next two scientists on our timeline. Very special person. So join me, please, in welcoming J.J. Thompson. J.J., is it okay with you if we call you J.J.? I know you've got a longer name, but is that okay with you?
Yes, you can call me JJ, nothing other than JJ. I like to be called JJ by you and by anyone else. JJ's my name.
Fantastic. I was hoping you would say that. Hey, could you tell us a little bit about your history of work and what drives you to do the work that you do?
Yes, I worked quite a bit in Cambridge, and I've been in the science game for almost my whole life. And I'm very fascinated by using scientific methods to discover more and more about the world around us.
Fantastic. That's what we're hoping to hear about. I know you made quite a few contributions that didn't exactly have to do with the model of an atom. Tell me, does your normal process as a scientist include experimentation? And how did you actually come to discover more about the atom?
Yes, I'm very fascinated by doing experiments, and I've done quite a lot of them. It is my trade, and that's what I do. A few years before I got started, there was a glassblower who figured out a way to make a vacuum tube, which we have filled in with various kinds of substances and gases, and then I shoot a cathode ray. Quite exciting, my dear, quite exciting. You'd be glad to know. It's a quite cool development, I must say myself. So we would take the cathode ray, as you say here, and project it through a tube, and if I placed a positively charged plate on the top and a negatively charged plate on the bottom, no matter, my dear, what kind of substance or gas was in the tube, that ray would end up projecting particles upward. What might that mean, you might say? Well, my dear, no surprise here. It's all about attraction. Ha ha! Chemistry is all about attraction.
So the cathode ray, which is essentially an electrical current, travels through some substance, and the cathode ray itself, the electrical current, whatever makes up the electrical current, is attracted to the positive plate. And that's connected to chemistry. Chemistry is about the attraction of the negatively charged parts in the cathode ray to the positively charged particles in the plate. Chemistry is about attraction.
Well, yes, that's what all of us think. We're working at the university, and we know that chemistry is all about attraction. What things are attracted in, and what do you find repulsive, my dear? What do you find repulsive? And these particles found it repulsive. Repulsion, pushed away from. Right here on the bottom. But they're quite attracted. quite attracted upward toward the plate that was positively charged. So, in other words, what that meant to me is that we have atoms. Thomas, as my more ignorant philosophical friend might say, not as indivisible as you might have once thought. Instead, these have smaller peats and particles that make up every atom.
So the way that the cathode ray behaved really was a breakthrough. It changed all of our thinking about whether an atom was really indivisible. How does this connect to what we've learned in the past?
Well, in short, my dear, what this means is that previously our beliefs that atoms are indivisible, we cannot chop them to smaller parts, is just flat incorrect. Scientifically, we have proved that there's a smaller piece and particle that can be projected either towards a positively charged plate and away from a negatively charged plate. And these indeed, and what I have named these, it's going to be fascinating, my dear, fascinating, my dear. I call them corpuscles. They probably remind you of nice muscles, but they are corpuscles, and you might feel quite attracted to the corpuscles. Yes, but what that means then is that these corpuscles have a negative charge, negatively charged particle. They're attracted. Very attracted, my dear, very attracted to the positive plate on the top of my cathode ray setup. Yes, so this is the first what we call subatomic particle. Yes, my dear, yes.
Well, I don't think I'm really attracted to corpuscles. Not me. I'm not that girl. But I am positive. And positive that I'm not attracted to corpuscles.
So, I have not quite single-handedly, but single-handedly, have discovered the very first subatomic particle. Now we know, because of me, that the atom is made up of smaller parts, and one of those parts has a negatively charged part. One subatomic particle is negatively charged. You want something to laugh about, Democritus? Yes. Oh, well, I've got a story for you, Democritus. How many philosophers does it take to change a light bulb? Answer me that. Answer me that. Oh, yes, me think. I was just thinking. I know it's a lot of work for you, old boy, but no. The answer is 3. 1 to actually change the light bulb, and the other 2 to argue whether the light bulb exists or not. Philosophers. Can't stand them, suckers.
I don't know if he's actually going to understand that joke or not.
And how about you, Quaker boy? How about you? Would you like to have a joke? Yes, you would you? Okay. Well, here you go. How many Quakers does it take to change a light bulb? Oh, a joke? Oh, I don't believe I know this one. Let me think here. Okay. I don't know. How many Quakers does it take to change a light bulb? Ha! Well, here's the answer for you, old boy. Quakers don't change light bulbs, they just fix them. Ha ha ha! Yes! Oh, yeah. Because they're so frugal. They fix everything. It's a Quaker. Surprised he even knows what a light bulb is. You're probably still using candles, aren't you, old boy? Aren't you? Yes, you probably are. Let's talk more about me.
Well, at the risk of playing into your ego, let's just talk more about JJ. Let's have the JJ show all the time, JJ. Tell us really, what does your model of the atom actually look like?
So the atom no longer looks like a ball bearing or a billiards ball or some other thing like that. We know now that it's made up of some positive stuff, and into that positive stuff is stuck some negatively charged corpuscles.
Do you know the modern name for corpuscles?
Whatever, darling, whatever. You say whatever you say. You saw, yes. Those are the negatively charged pieces that I have discovered in my cathode ray tube. There they are. There they are, darling. You know you love it.
Okay, you got me. I do love chemistry. I do love all that stuff. And I really love how we can take something that is so small, we can't see it, we can experience it really and every day, and we compare it to something that we can see every day. And your model of an atom had a very special comparison. Could you tell us about that?
Well, it was called the plum pudding. Plum pudding. But what I have here is tapioca pudding, which is pudding plus a little bunches of what appears to be quite disgusting bits of pasta. Yes, a pasta in the pudding. Pudding pasta. Pasta pudding? I don't know, darling. I don't care, darling. What it is it's the idea that all the pudding is the positively charged part of an atom, and all of the tapioca, that's the corpuscles. And nowadays, yes, I know, darling, yes, I know. I know we call them electrons now, darling, I know. Yes, I know. Darling, are you feeling attracted at all? At all, darling? No. Nope. It would be very weird if I was, because you seem very familiar to me and not in a good way at all. So we better just move along from today's video and prepare ourselves for the next video. We'll be talking to Ernest Rutherford, and I think you're familiar with him a little bit, JJ, aren't you? Well, if you must, you must. Rutherford, blowhard. Can't stop talking, that guy. Ha!
This is Mrs. Singer saying good day, good night, and goodbye.
This is JJ Thompson signing off saying, remember, it's all about the attraction. Ha ha! You should come on over to Cambridge sometime, darling. I'll take you out. We'll go out on the town. It'll be fantastic. You're gonna love it.